Okay, let's look a little closer at the energy in a simple harmonic oscillator, which we have argued generally will look like a kinetic energy function, 1 half mv squared, plus a potential energy function, which is parabolic in nature. Now remember that total mechanical energy is a constant, right? Total mechanical energy is a constant, so E equals a constant. So let's just think about what does a graph of let's say, what's a graph? Well, here, let me go to a new page. Oh, a joke. Okay, so let's graph energy versus position for a simple harmonic oscillator. Just think about a mass on a spring, which is oscillating about x equals 0, or a pendulum, which is oscillating about, we can call it x equals 0, or theta equals 0, and we would be graphing energy versus theta instead of energy versus x. But we can just give the angle variable x, call it x. Okay, so what does the total energy look like? You know what total energy looks like, right? Total energy is a constant, so the total energy, whoops, I meant to draw that a different color. The total energy would look like that. It would be a constant. The oscillator goes between some x max in the positive direction and some x max in the negative direction, so hence I draw the energy where I drew it. Here, I'll even do this. X max, or A. I guess I can just call that A for the amplitude, and over here it's a distance A in that direction, amplitude. Okay. All right, so what does the potential energy versus position look like? Potential energy versus position. It's a parabola, right? And the potential energy, if we look at it, it's U goes as 1 half kx squared. Sorry, there's some extra dots on the screen here. 1 half kx squared. So you should be able to graph that, and you will find that the graph looks something like this. It's a parabola. There we go. It's a parabola. And the shape of that parabola is defined by the arbitrary constants, 1 half k. That's not a minus sign in the energy. That was just an extra dot on my screen. Hold on a second. Okay, so what does the kinetic energy versus position look like, right? What does that graph look like? K versus position. Can you imagine what that looks like? Well, because the total energy is a constant, then the kinetic energy plus the potential energy, whoops, this has got to be A. We can just draw that. X equals A, X equals minus A. I guess I could draw that as minus A, yeah. So we've got, it goes from minus A to A. What does the kinetic energy look like? Well, when the potential energy is a maximum, kinetic energy is a minimum. And when potential energy is a minimum, kinetic energy is a maximum. And so it better look like this. It's a parabola. It's the upside down parabola. Okay, so those are our energy functions. And I guess one thing that, the way I sort of think about this, and I don't know if this is useful or not, is imagine the potential energy function is actually, right, a hole in the ground or a bowl or something like that. And the whole idea is that that the mass, right, is trapped in this potential well. We call these a potential well, right? It can only go so far, and then it stops, and then it goes back again. So it's trapped in a well. That's the physics term, is trapped in a potential well. And you can see that by imagining this is a bowl, and you were to put a marble anywhere on this bowl, and you just start it from rest. And what happens to that marble? The marble is going to go down and get up some speed so that it goes up the other side, but it'll never escape from the bowl. It'll go back and forth in those positions. So that's what we mean by a potential well. Can the mass ever escape? Can it ever get out of this harmonic oscillator function? Yes, it can. If we give it enough energy, right? If we give it enough energy, we can shoot it out of the potential well. In practice, what's that going to be? That's going to be like giving it enough energy to break the spring, or giving enough energy to break the pendulum or spring, essentially, right? We could theoretically give it enough energy such that that potential function, the gravitational, let's just say the potential function of the spring constant is no longer strong enough to keep it oscillating back and forth about equilibrium, in which case we really have just broken the spring. So yeah, we could give it enough energy, but as long as we're within the realm of the strength of the spring, we are stuck in that potential well. Okay. What about non-parabolic potential energy functions? We can have harmonic oscillators that are not parabolic, right? And that's just not simple, right? It's simple. The simple harmonic oscillator was the one that was that had a parabolic function, and we understand how to analyze that function. But what about potential energy functions that are not parabolic, but they're still harmonic oscillators, right? So a non-simple harmonic oscillator. What the argument that I want to then make is that all potential energy functions for all bound state potential energy functions, all potential wells, all harmonic oscillator functions, these functions which curve upwards, which indicate that a mass is stuck in that potential well, all functions approximate to a parabolic function. That's the argument I want to make. Next is that all functions approximate to a parabolic function. And what I mean by all functions, I mean all functions that have curves in them. And this is just a mathematical fact, is that all curves can simplify to parabolic. Simplification might be accurate or might be a little inaccurate, but all curves simplify. I mean, you can certainly have a function, a potential function that is not a curve, right? That's just a straight line or something like that. And that does not simplify to a parabola. I'm trying to think of what potential energy has that. But if we've got a bound state function of some sort, like we have here, if we've got a potential well, but it's not parabolic, can we approximate it as being parabolic? And the answer is yes. We can always approximate it as being parabolic. And the answer is we can always approximate it as being parabolic as long as we look close enough to the bottom of the well. What do I mean by that? Well, this is a mathematical argument, right? The mathematical argument is let's Taylor series expand our potential energy function. Let's say we have an arbitrary potential energy function, U as a function of x. And we Taylor series expand that about it's zero, right? It's x equals wherever the lowest, its minimum, sorry, is what I'm trying to say. Taylor series expand it about its minimum. Let's just take something like, for example, let's just say it's some potential energy function like that, and that's not a parabola. Let's say it's even just a circle. Let's just expand it about x equals a. We can do the Taylor series expansion as you learned in math, and what I want you to see is that if x is close to a, right? If we're looking close to a, if we're just looking at the shape of this curve close to a, if x is close to a, these terms, x minus a squared, x minus a cubed, are small, and so they're small compared to 1, or small compared, each higher order term is small compared to the next because it's a small number squared, a small number cubed. So the closer we look, the less significant the higher order terms are. It's a lot like the binomial expansion, right? So if we say that x is equal to a, then indeed it's just a point, that u of x can be evaluated as a point. Well, that's not useful. You say, but then the next order term is a line, right? That at the bottom of this well, if we look close enough, it looks pretty flat. That's what that says. If we look really close, it looks pretty flat. But then this next order term says, it curves up like a parabola. If we look close to a, but a little further out, it curves up like a parabola. And then the third order term says that, okay, it might have different curve, but if we look close enough, the point is if we look close enough in, that every curve, that means we got to look out farther than where it looks like a point or a straight line, every curve starts looking like a parabola, because this is the parabola, right? Every curve starts looking like a parabola. The farther out we look, right? The farther out we look, the less it may look like a parabola if it's not a parabola. But as long as we focus in, every curve looks like a parabola. And that's what the Taylor series expansion tells us. So we can approximate every potential energy function as long as we're close to the bottom of that well. And if it's not a parabolic function, we can still approximate it as a parabolic function. Oh no, another bad math joke. So the point we're trying to make is that not only simple harmonic oscillators, but all oscillators can be approximated to have a potential well that looks like the 1/2 kx squared function, the parabolic function. And all simple harmonic oscillators, to some extent, have this kind of energy dependence. Okay, that's all we got for simple harmonic oscillators, or all harmonic oscillators, and we're going to move on to waves. Have a happy day.